Good morning, everyone. Welcome back. Someone recently introduced me to ScreenFlow, and I thought it would be fun to record some tutorials here. So let's get started. This is the blog post that I wrote over this weekend, summarizing different laws that we commonly come across in scientific computing. I especially focus on the ones that are related to computer architecture trend, performance, or efficiency of parallel applications. The first on the list is Amdahl's law, and if you have done parallel programming, most likely you have heard this multiple times. It says if application is parallelized using multiple processors, the achieved speedup is limited by the inherently sequential part of the application. In 1972, Gordon Bell stated, roughly every decade, a new lower-priced computer class forms based on a new programming platform and network. This results in a new usage and establishing a completely new industry. This is commonly referred as Bell's law. In 1974, Robert Dennard and his colleagues explained how CPU manufacturers were able to raise clock frequencies without significantly increasing overall power consumptions. They stated, as transistors get smaller, their power density stays constant, so that the power usage also stays in proportionate to the area. This is referred as Dennard scaling. In relation to computer performance and its cost, Herb Gross stated, computer performance increases as the square root of the cost. In 1993, Neil Gunter presented conceptual framework for understanding the scalability of the system. He stated the relative capacity Cn is equal to N, which is the number of physical processors, divided by 1 plus alpha multiplied by n minus 1 plus beta multiplied by n multiplied by n minus 1. Here, alpha is level of the contention in the system, and the parameter beta is coherency delay in the system. John Gustafson in 1988 addressed shortcoming of Amdahl's law by showing how applications can retain the scalability on the large computing systems. This law says if you apply P processors to a task that has a serial fraction f, the speedup will be equal to f plus P multiplied by 1 minus f. As you can see, f remains constant because it's sequential part of the application, but the rest of the application scale with respect to number of processors P. Jonathan Koomey observed following trend since 1950s regarding the energy efficiency of computers. At a fixed computing load, the amount of battery you will need will fall by a factor of 2 every year and a half. He re-examined the data in 2011 and found that this law had slowed to 1.5 years instead of 2.6. John Little in 1954 provided a simple and intuitive approach for assessing the efficiency of queuing systems. This is summarized as the long-term average number of customers L in stable system is equal to the average arrival rate lambda multiplied by the average time W a customer spent in the system. In 1965, Gordon Moore, co-founder and CEO of Intel, made following observation regarding the transistor density. The number of transistors in a dense integrated circuit doubles about every 2 years. The period is often quoted as 18 months because of a prediction made by Intel executive David House. This is commonly referred as Moore's Law. Pareto principle is not specifically related to the computing, but we often hear this in multiple contexts as 80-20 rule. It states, for many events, roughly 80% of the effects come from the 20% of the causes. In computing, the Pareto principle can be applied to optimization efforts. For example, 80% of the improvement comes from 20% of the efforts. Rock's law is related to the cost of production of semiconductor chips and named after Arthur Rock. Arthur Rock was a prominent investor who heavily invested in Intel, Apple, and other companies in early days. This law states the cost of semiconductor chip fabrication plant doubles every 4 years. The second last law on this list is Sun and Nee's law. This is also referred as memory-bounded speed-up approach. It says, as computing power increases, the corresponding increase in problem size is constrained by the system's memory capacity. And finally, Watt's law, which states the software is getting slower more rapidly than the hardware is becoming faster. And I think this gap between software and hardware is becoming wider and wider. That's all for this post. Thanks for watching and see you next time.